Great, thank you. Yeah, so I'm going to talk about diviner and uh, temperatures within the candidate regions. I'm highlighting some of our relevant data sets. Next slide, please. So, yeah, I'll do a brief introduction to diviner for those on the call that aren't familiar with the instrument and what our data products look like. And I'll focus on specifically our gridded products in the polar region, since that's the most relevant to Artemis, and then highlight some of the maps, specifically maximum and average temperatures that can be used to infer the cold trapping potential in these regions for water ice. Okay, next slide. So diviner is one of the 7 instruments on LRO. As Maria talked about earlier in the session, we have 9 spectral channels that measure both the reflected visible and emitted infrared out to about 400 microns. And so the channels that are most relevant for characterizing polar temperatures are our thermal channels out at the longer wavelengths, and that enables us to characterize the brightness temperature over the full range of temperatures that we observe. So each channel has 21 detectors and an array that nominally are native pointing and sweep along with the spacecraft in a push broom configuration. And so each observation generates an RDR record, and so that includes a calibrated radiance along with all the potential information you would want to have to do something useful with that measurement. So there's a total of 33 fields in total associated with each RDR record. And we have been operating near continuously since the beginning of the mission in 2009. And so we've accumulated over 500 billion observations at this point. So as you can imagine, this is a pretty daunting data set to tackle if you're not familiar with it. And so a lot of effort over the last few years has been spent trying to think about ways to make this data more accessible to the greater community. And so I've been working on a lot of sort of higher level data products that remove the ability to the computational expense for doing useful things with this data, making maps, making it easy to get into things like ArcGIS and QuickMap, things like that. Okay, next slide, please. So when we talk about temperatures in the polar regions, we really need to address seasonality. It's really important. Unlike at lower latitudes where we really only worry about diurnal temperature variations, seasons can be actually a big driver of the temperatures. And I'm showing that here where I've taken a chunk of our data and created some maximum temperature maps, and I've divided it amongst different subsolar latitudes to highlight how the temperatures vary through the seasons, through the draconic year. So in the summer, these maps really highlight the PSR. So anything that shows up in the cool temperatures on this color scale are the PSRs. And then you can see that as the sun gets lower on the horizon, as we go into winter, areas that are perpetually shadowed throughout lunation grow substantially, and the overall temperatures get much lower. So the PSR temperatures also get much lower. And so that elevation of the sun in the sky is really important for scattering that light into the PSRs. Next slide. So yeah, so you can actually see this here in this plot at the bottom in Hayworth and this area we're calling Region 5. That you can really see that seasonal signal there is actually the dominant signal. So in many of the PSRs, actually the seasonality is more important in many respects than the diurnal variations. So probably the product that's most relevant here is what we call the polar cumulative product, where we've taken all of our data and compiled it into a gridded data set so that you can pull out temperatures with different times of day and different times of season. So these are all been at 240 meters per pixel and a stereopolar projection down to 80 degrees south. And so the first version, which we call the diurnal version, really emphasizes more of the diurnal variation. So we have 96 bins of local time or subsolar longitude to describe the diurnal variations in temperatures. Then that is split into 2 seasonal bins defined by whether the sun was above or below the equator to define a summer or winter season. More recently, we created a new version of this data set in a project in collaboration with Norbert Schurghofer uh, where we reduced the number of diurnal bins to 24, but then increased the number of seasonal bins to 6 to highlight the seasonal variations. And we then define the season by an LSOBES, or the ecliptic longitude of Earth and Moon system, that defines the draconic year. So we now have an angular description of the seasons. And these seasons are actually slightly shorter than the actual orbital period due to the 18 and a half year precession. And all this data is available on PDS. We also host it on our team website, and many of the derived maps are on QuickMap as well. Next slide, please. So here's an example of slicing through this data set and pulling out some temperatures of the region around the South Pole for different subsolar longitudes. So this gives you a nice snapshot of temperatures for a particular solar location. Next slide, please. So here I'm focusing on the connecting ridge and its extension here, highlighting maximum temperatures, average temperatures, and then the percent of the year that a particular spatial bin was below 110 Kelvin. So I picked 110 as a cutoff because that is often quoted in the literature as sort of the volatility temperature of water ice. So if you look at the lower right figure, this is a figure that Leo Rubinenko put together for me for a book chapter we recently submitted, showing the sublimation rate as a function of temperature. And so as you go from, say, 150 Kelvin down to 110, sublimation rate decreases by 6 orders of magnitude. So by the time you're around 110 Kelvin, sublimation rate is so cold that water, any water molecule that lands on that surface is effectively cold trapped for billions of years. So it's sort of a nice cutoff. So when we look at the maximum temperatures here on the lower left, any pixel on this map that is basically blue are areas that never reached or never exceeded 110 Kelvin during the year. And so these are areas where you potentially could be cold trapping water on the surface. Now, if you look at greater depth, so the upper right figure, these are temperatures actually taken from a thermal model of an area in the polar region. But you can see that even if the amplitude of temperatures, so this is showing minimum, maximum, and average temperatures with depth, and that amplitude at the surface is damped down pretty quickly. And so that sensible heat that is conducting down into the subsurface doesn't really go very far. And so the maximum temperatures that are experienced at depth are much lower. So the average temperatures are fairly representative of the temperatures beneath this thermal skin depth. And so when we look at the average temperatures, we can see that areas that are below 110 Kelvin are actually much more extensive. And so that would suggest that there are at least the potential to cold trap water at depth over a much larger area within this region. Okay, next slide, please. And then, when we look at the percent of time below 110, this gives us a good idea of areas that are getting a lot of shadow or permanently shadowed versus areas that have minimal shadowing. So these ridge tops, right, in this map show up as blue, and those would be obviously optimal areas for illumination conditions. And I pulled an example of one location there on the ridge, showing how the temperatures vary with time of day and through the seasons. And so when we look at the summer, and this would be occurring, say, in January of 2026, temperatures are all consistently high, sort of around 150 Kelvin or above. So these are areas that are persistently warm and illuminated through the summer. And then as we go into the winter months, on the left half of that plot, you can see that the temperatures vary much more, and the illumination conditions are clearly more complicated as shadows are starting to sweep across this ridge. Next slide. Here's another example of two more of the sites and the distribution of temperatures. So, Diviner can give you a quick snapshot of, what the potential for cold trapping water is within these regions. If you look at along the ridges here, you can see there are small PSRs in there, but they're generally fairly warm and probably too warm to cold trap water ice. If we look at the average temperatures, there are patches that are below 110 Kelvin where you could potentially have some cold trapping of water in the subsurface. Next slide. Malpert Massif is, I want to highlight these two because these are represent sort of the lowest and sort of the greatest potential for cold trapping water. Malpert has very few areas that are really, all the PSRs on that ridgeline are really too warm at the surface, at least at the resolution of Diviner, right? So 240 meters per pixel. New patches that are in average temperatures that would suggest that in subsurface you could potentially have stable conditions for water ice, but it's much more limited. Now, if we, by comparison, look at Faustini, you have a lot more options for potentially finding water ice. There are many cold PSRs in the region on the surface, and then the subsurface. Over half that area, surface area, is actually below 110 Kelvin. So this would be considered one of the more favorable sites if you're going after volatiles. Next slide. For sake of time, let's skip this one. So here I've sort of ranked them from sort of lowest to highest as far as cold trapping potential, just purely based on the diviner temperatures. So you can get kind of a snapshot of which areas have the greatest potential for cold trapping. This doesn't. I haven't done a detailed analysis here of how accessible any of these areas are. So, but for the most part, most of these areas have regions within the subsurface that are likely stable, thermally stable for water. But many of them are fairly limited on the surface temperatures, with Faustini being one of the better candidates. And last slide, next slide. So here's where the data is available. The Diviner website has a nice big button on it. You can just link directly to the PDS archive. And there we also have GeoTIFFs, GMT formatted binaries, ASCII files of all this data, and many of the derived maps, like maximum average temperatures that I showed, and additional derived maps such as sublimation rates that Norbert Schurghofer generated from these data sets. So that's all there. Many of these maps are also on QuickMap. So with that, I will end it there.
All right, thank you so much. That plot at the end is really fascinating.